Okay, so let me start by thanking the organizer for giving me the opportunity to speak here. And it's really nice to be back with this meeting, which used to happen before the pandemic regularly. So I'll be talking about something related to talks, some other talks today and earlier. Uh, so let me first acknowledge the person, student who has done the work, Shibram, who is here. And if you can find the details of this work in this archive. Okay, so I'll be talking about something which is related to this, but exactly not this. So this is a thing to do with what is called measurement-induced phase transition. So the typical setup, which is easy to explain, which is what Harshini was also showing, is that so you start. So it's what are called these random quantum circuits. So essentially, you have some states, and you evolve it with some, let's say in this case, some 2-qubit unitaries. And then in between also you do some measurements with some fraction of bits, these lines. Okay, so you do measurements with some fraction of size, and that defines some measurement rate. Now in this kind of systems, if you had only unitary evolution, then you will have entanglement growth as was discussed. But if you do measurements, then it sort of hinders this entanglement growth, and if you do too much measurements, then it can even destroy this growth or make it slower, and can lead to a very different kind of states. And this is not only limited to this kind of quantum circuits. People have looked into other models like non-interacting fermions, interacting bosons, Luttinger liquids, etc. With different kinds of measurement strengths, measurement rate, measurement strength, etc. And you see both with projective and weak measurements, and you can see this kind of transitions. A typical representation of this here. So this is looks into entanglement entropy at long time after you have evolved it sufficiently long time. Then you see that depending on this measurement strength, you can have a transition where the entanglement entropy as a system of as a function of system size, if you have low measurement rate, grows as a volume law, as a in one dimension it grows as L, and if you have more measurement, then you saturates to a constant, which is the area law, this, and so essentially you get a transition. So this phase that if you get at low measurement rate, you can call a chaotic phase because it has large entanglement, has volume law. And when you go through this transition, you can have something called a non-chaotic phase. So you can call this transition as chaotic to non-chaotic phase transition. So now what I am going to ask, motivated by this, that can there be a classical limit of this measurement-induced phase transition? Okay, so this is essentially the summary and outline of my talk. What I am going to discuss, I will start very briefly discuss a quantum measurement model of continuous weak measurement, and I will show that if you take certain kind of classical or semi-classical limit, it actually maps to our very old and favorite stochastic Langevin equation with a fluctuation dissipation noise where the strength is actually controlled by the measurement strength. And then I will show that taking some example of some coupled anharmonic oscillator, I will show that if you subject this oscillator chains to this kind of measurements as a function of measurement strength or the noise or dissipation strength, you can actually get a transition where your Lyapunov exponent of this some semi-classical or classical limit goes from positive to negative as a function of measurement strength. So you will have a chaotic transition. Okay, so this will be the limit of a measurement-induced transition in the classical limit. Okay, so let me very briefly discuss the quantum model of weak measurements. So what you start with, imagine that you have some system which is described by some Hamiltonian, some oscillators. It can have anharmonic terms, so some general potential. Now what you do is you do weak measurements on this system at discrete time to start with, at interval of time tau. So essentially at this times you couple these oscillators to some ancilla or some meters, and then what you do, you measure projectively the meters, not the oscillators. So this is the protocol. So essentially you have measurement at this discrete time, and between these two measurements the system evolves with this Hamiltonian. But then at time Tn, just before time Tn, you are ready with your meters or the ancillas, which are prepared in a Gaussian state, and where the important parameter is the width of this Gaussian, of this ancilla, which is sigma. And then at time Tn, you make them interact through this interaction, and then eventually at Tn plus, you measure and projectively measure this meter, so they collapse into some projective state and that gives you some readings. Okay. So now what we can, I'll skip the steps. So you also have to take into account some feedback and all, but essentially you are going to talk about this limit where this measurement that you do is very weak. So this weakness is measured by the width of the Gaussian. So if the Gaussian has very large width, it's extremely weak, but you do the measurement too often, too frequently, so that you take tau going to 0. And you want to take the limit that this sigma tau is finite, so that defines the inverse of that actually determines the measurement strength. So in this limit you can actually formulate it as a path integral, a Schwinger-Keldy's path integral. So again the details is not important, but what you can show that if you take a certain type of classical limit, so you have to take the classical limit carefully, you have to scale certain parameters in a certain way, then what you can show that this leads to our very old stochastic Langevin equation that we have studied for so many years. And here the thing is that you have noise and dissipation and they are related by a fluctuation dissipation relation with some effective noise strength which is determined by the measurement strength, and the effective temperature which is determined again by the quantum parameter h bar. Okay. And since it's a Langevin equation, it will lead to a non-equilibrium steady state which is determined by this effective temperature which is determined by the measurement and quantum mechanics. Okay, so this is the thing. So now what we are going to do is we want to see that whether there can be a chaotic transition in this classical limit. So what you find, so what we are going to study is some coupled oscillators. So for example, some generic type of quartic oscillators which are coupled like that, or some integrable Toda chain. And then what you are going to do, you are going to do measurement, going to study this Langevin equation, very standard Langevin equation, but we want to look at chaos. Now typically the way you look at chaos is you look at two trajectories and then let's say initially they are slightly different. For example, in this oscillator, one of the oscillator I perturb a little bit like Stitodi was discussing yesterday, and then you try to compare these two trajectories. Now here these are noisy evolutions, so you have to make the noise exactly correlated to have a meaningful definition of this trajectory divergence. But if you do that and you can look into some noise correlators and you mask and you start with some initial condition which is this long time steady state, as I said, which is determined by some temperature, and you ask in this case whether you have a Lyapunov exponent or not. So this is the result. So what I am looking at is this classical OTOC, the protocol I described, and here what I am showing here is the OTOC at this site where you have given the perturbation, and this is for a fixed noise strength as a function of interaction. You can also study at as a function of gamma, gamma, and as a function of u. Sorry, you can fix the u and you can study as a function of gamma also, same results. So if you have low interaction, what you find that this OTOC actually decays with time. So basically it has a negative Lyapunov exponent. If you now go on increasing the u, you start getting a positive Lyapunov exponent. So there is a transition from positive to negative Lyapunov exponent at a critical value of u, or in other words, if you fix u, you can get a transition at a critical value of the noise strength. Okay, and you can also look at light cones, the spatial information, and you can also show that there is a similar transition in the butterfly velocity. So the light cone, after you go into this non-chaotic phase, is completely destroyed. Okay, in fact you can look into this velocity and you can do a finite size scaling, and you can find that this has actually nice finite size scaling with critical exponents. However, these critical exponents do not match with the standard thing people expect, like what Sitodi discussed, like directed percolation or Kardar-Parisi-Zhang type universality classes. If you look into integrable model, there could be more interesting thing, because integrable model, when you have zero noise strength, it is non-chaotic. So here when you initially use noise, it can give chaos, but eventually it destroys the chaos. Okay, so there could be non-monotonic behavior. So essentially, okay, so this is what the summary that I started with. So this transition that I described is actually well-known transition. It is called stochastic synchronization, and what we are showing is that this transition happens here as a function of measurement strength in a model of quantum model in this semi-classical limit. Okay, thanks. Yeah.
response. I mean, can you explain, I mean, what is measurement strength exactly? Because in your case, the noise is proportional to measurement strength. I find that's very interesting.
So the measurement strength here, so I am measuring weak measurement, right? So initially you prepare a wave packet. Now if the wave packet I make very broad, then you can have any, when you do projective measurement, you can have any value of x. So that is like the strength of a measurement, because if you take a delta function, like I took a Gaussian, right? If I take the delta function limit, that will be like projective measurement. So that defines the measurement strength, how broad wave function I prepared for the meter. And then another thing is how often you do the measurement. So the ancilla, yes. So that's what determines the measurement strength, how strongly you do the measurement. So you can tune it from weak to projective measurement.
The broader the weaker.
Broader the weaker, yes.
So any other question?
So you see a transition in this OTOC or whatever, but like, is there some in terms of physical observables? I mean, is there something which shows a transition?
No. So actually, if you look at any standard correlations, diffusions, there is no transition here. So only if you compare two copies, there is a transition.
So no physical observation.
No physical observation.
Okay, so let's thank the speaker.